So this is the second video on my channel. This is also a video that I'm raising for something that I'm working towards. I won't specify what, but so in this lecture, just put it in that way, I'm going to be giving an introduction of analytic number theory in its entirety, I think along the way I'll introduce the study of multiplicative and additive functions, and completely multiplicative and additive functions, and then an introduction to the prime number theory, a specific class of functions, such as, for instance, the von Neumann function, and then a Bell summation. And this is just an introduction. In my next lectures, I will hope to get into equidistribution, Gaussian sums, and then actually like admissible sets and GPY weights for the distribution of primes over C of gaps. So this will be my first video. But yeah, so this will be on analytic. Analytic numbers. Okay, so what just number theory is really in its entirety, it's just the study of just what numbers are really in their entirety, like just specific properties like parities, for instance, within elementary number theory, which are things that are maybe briefly brought up in primary school, but are talked about in much more depth in fields, in number theory. And then analytic number theory is more of the study of, I would say it's a subfield of number theory, but it more deals with, I think one of the main things that it deals with is prime numbers. Which is where my research has been heavily centered in, namely the supremum or upper bound of weighted gaps, and like working over extension fields. So, but that's I digress. So the first thing I will be going over is the set of functions f going from the natural numbers, the set of natural numbers with any normal subgroup existing over this, to the complex numbers. So this is essentially just an extension of this, and it's set I will not be going into the logistics just yet, but yeah. So let's say you have this mapping f that maps every element of the natural numbers, which is positive integers, to complex numbers. If you have such, then you can take, then this will define multiplicative. And this actually just in its entirety defines arithmetic functions. So I won't leave that here just so I have more room, but that's essentially what this class of functions defined, in which you have these subgroup functions. Multiplicative. Okay, so function f of, let's say, f composed of, let's say, two elements, say AB, for A, B elements of any subring with a residue class modulo A or B. If you have such for, these elements, I can't speak right now. For these sub-elements of n, this could be like 1 and 2, or 5 and 8, or something of sorts. If the function set of multiplicative is, if it's titled that if this relation is equivalent to f of A by f of B. So this has its applications. I can give a quick example. So e.g. on the divisor function, d of just n is of course just equivalent to the quantity of divisors of a specific integer n for n a natural number. So namely, if I, let's say, have 6, number 6, I can take that to be equal to d of 2, or the divisors of 2, by the divisors of 3, right? Because by the fact that this is multiplicative, I can just combine this, and this will give me d of 6. So, and this is obviously 2, that's just 2, and 3 is just 3. So that will give me d of 6 equal to 4. So, right? And also, you can say that d of any prime p is obviously just by observation is equal to this here. So that essentially is the whole gist with multiplicative functions, and they will come in handy when we start investigating like Chebyshev's functions, and namely their properties and like reducing functions, yeah. So now we have the term additive. So a function f, let's say ab again. Function f of composed of ab is titled additive for, again, a and b element or natural numbers. If if f composed of a by b is equivalent to f of a plus f of b. So there's also, I think, for instance, to give maybe a lesser example, I know in like functional equations with like mathematical Olympiad, to give an example, I'm trying to think. Probably this is, I'm not giving one directly related to number theory just because if you're looking at this for the first time, to give another example, there, like within functional equations, you may have heard of like Cauchy's additive equation, which gives that this, function composed of just two numbers, if you will, is equivalent to the sum of them. So these individual elements. So hence, to give another example, you can take the function omega of n, which takes the sum of actually these divisors, and because of the fact that you're taking the sum over all divisors of n, then hence this is equivalent to maybe because of the fact that you just have the singular element, that I can't decompose this currently, hence n is irreducible over n. But if I, let's say, to give an example, have, let's say, how about 6 again? So again, this is just the same thing as writing omega of 2 by 3. So this is the same thing as writing omega of 2 plus omega of 3, which will give, hence, this omega. So now that I've established that, I will now go into, and sorry, I'm trying to describe this in just as good of just like English as possible. But yeah, so. Okay, so the next thing I will go on to is a Bell summation, which comes in handy a lot within number theory. So a Bell summation, or also known as partial summation. So the kind of basis behind it is that suppose you have, suppose for sum from n all the way up to some bound x, let's say, it's not the Dirichlet character, of an by some function that need not be multiplicative or additive, f of n, you can, and for f of n analytic, or namely that there does not exist any singularities within n, this can hence be represented as a of x by f of t minus the integral over this over this interval 1 to x, which can be extended to from 1 to x to 1 to epsilon for epsilon large of a of t of f prime of t dt. So, and just by the way, if you're confused on, oh, well, how can you compute this a of x that just came out of nowhere? Well, there's actually a nice trick, if you will, that you can take a of x equal to the sum and all the way up to, again, some x of a sub n. So, which also comes in handy a lot with Dirichlet series. When you're trying to continuously decompose a function into maybe something maybe that's not a summation, but actually in respect to an integral. So it comes in handy with that. So now that is essentially the basis behind that. And with that, I can now move on to and that's not the entirety of it. There are other things like with the Dirichlet series specifically, you can let, so that's an over n to the s, and that's actually equivalent to a of x over x, if my memory is not mistaken, I think maybe like x to the s plus x to the s minus s or some s by the integral over this bound of the fractional part of t over t to the s. Sorry, not the fractional part. Like you can choose some bound, maybe like log of t plus big O of 1 over t to the s plus 1 dt. And I'll actually show you where that comes from. And maybe a next video, because this video is already getting kind of long. But anyway, so that's the basis behind that. So now, let me just clean this up. And let me move on to the prime number theorem. Okay, so the prime number theorem in its entirety states that the limit as x approaches infinity of pi of x over x log of x is equivalent to 1, meaning that pi of x is asymptotic to x over log of x. So in its entirety, and this is also for pi of x in prime counting function, or that denotes all p up to some x. So what this essentially describes in its entirety is it gives kind of like an approximation as to kind of just the pattern in which all primes sequentially increase. And because of the fact that, just by the way, because of the fact that pi of x is strictly monotonic increasing on this interval, in this case I can actually extend the 2 to epsilon, for 2 being the infimum of this given set. You can extend this all the way to infinity, I guess, or for x large. But hence, because of that, this is hence always positive. And what this actually, kind of a few results came out of this. One being that, let me first write this, is x log x. Okay. So what came out of this was that actually there's kind of a rough approximation to kind of the p plus 1, p plus 2, to, p all the way to pn term within a given set, like to the epsilon or x in that case. And that can namely actually be given by 1 over log of x. So that can be immediately deduced from this. So, and hence this also gives a result that theta of x is asymptotic to x, and same with psi of x. For theta of x being equal to the sum for all primes p up to some x. And actually this can also be given for x, can also be given as the n plus 1 prime over log of n. So that's the same thing. Log, actually a p in that case, right? of log of p. So, and then psi of x being equal to the sum over just all n, in this case up to x, of the von Mangel function of x, or equivalently x log x. Okay. So, and just by the way, the von Mangel function is given by this piecewise function, namely it's equivalent to log of just, I guess, x in this case, if x is equal to, or I can give it as the infinite product of all primes k up to n for a unique factorization of x, and then 0 otherwise, or if that does not exist. So, in that case, now that we have that out of the way, we can establish a few properties. So first of all, we can establish the fact that by Chebyshev, the sum of log of p over p for all p less than or equal to x is equal to log of x plus the big O of 1, which namely big O of 1 is actually, it means that just in its, well, big O notation, essentially if you have like some function f of x is equivalent to big O of g of x, and that essentially means that the modulus of g of x is greater than or equal to some constant m in which such is bounded by, is equivalent to that constant, let's say m, by f of x. So this is essentially saying that this is bounded by 1, really, in its entirety, plus this log of x term. So if you notice, actually, this can also just be given, this is summed over, this is really also, if you notice, as p goes to infinity, this actually just tends to 0, hence you'll get something that resembles this log of x plus big O of 1, right? Or sorry, p. Oh, oops. Not sure where that came from. Okay. But anyways, so by that, this will come in handy in a bit. We can hence establish the fact that by using a Bell summation, that for I can establish the fact that the sum, and I can actually notice that theta of x, maybe write n. X. This is equivalent to by a Bell. So I can take my a of x maybe to be, I can take my a of x to be, to just be this theta of x. Right? So then hence I can take my f of x in this case to be equal to 1 over x. And that will come in handy in a bit. So hence by this, I can take, this is equivalent to theta of x over of x, right? Minus the integral from 1 to x, namely for some p element of this and such that there exists a non-empty topology over all sub-elements that form a ring over all binary operations. 1 to x. And hence by this is actually equivalent to my a of t, which in this case I can set to be equivalent to the sum over, this is a of x is equal to the sum over all a of n. So for a of n equal to, so this gives theta of n, but hence by decomposing that into a double sum in respect to log of n, I will actually just get log of n over, log of n over, log of t over t squared dt, right? Because if you're taking f prime, you'll get 1 over x squared. you get negative 1 over x squared. So I apparently cannot do basic single variable calc, so that turns into a plus. I don't know what's going on in my brain. Jesus. Sorry. So anyways, I can now see that because I can notice that this theta of n for this actually is essentially the equivalent of theta of p, or this actually just being the equivalent of p less than or equal to x of theta of p over p. Because, right, so this actually is essentially the equivalent of saying that theta of x over x plus the integral over from 1 to x log of t over t squared of dt is equivalent to this log of t term plus the order of, and I can actually just write this in respect to x. Okay, so this I can actually, as x tends to infinity, this tends to 1, hence that will cancel out, right? So you can take the log of, so these will actually cancel out for x an element of this gap, and hence you will be left with the integral from 1 to x of log of t over t squared. And now if I take log of, actually I meant theta of t. I meant theta of t. I'm so sorry. What did I do? Fudge. I'm sorry. I don't know why I did that. I pulled a move. So that's theta of t. So now hence I can decompose theta of t for theta not equivalent to an irreducible character, meaning that there exists a trivial representation of such over an extension field in n, such that theta of t is equivalent to some epsilon by n minus the order of 1. Sorry, plus this order of 1. So this just gives like this essentially, actually I can write this as t. So this essentially gives that you have this integral from 1 to x of epsilon t plus the order of 1 over t squared. So dt. So now if I notice, this order of 1 actually bounces, right? Meaning that this essentially has to be equivalent to 1, right? Because it can't be 0 because it's strictly increasing, right? But since for the fact that it's big O of 1, then I think this has to be equivalent to 1, hence, and for this term right here, you get just 1 over, if I can actually do basic arithmetic, you get that, you just get epsilon to the t to the negative first, or you'll get epsilon over t, or you can pull epsilon out because that's constant, and you get epsilon by ln of x, right? Because ln of 1, that's 0. So you get epsilon by ln of, and I can actually just set epsilon to be equal to x, so x minus order of 1. Sorry, that should have been minus. And then, hence this gives us, and sorry, there's also a minus x here. Right, so this actually gives, this gives actually this original sum, namely theta of p over p. And actually, I can see that as x grows, this will actually all tend to 1 because of the fact that because the order of 1, sorry, I keep on saying I said the order of 1, I'm sorry, I meant big O of 1 can be, Yes. So as this tends to just infinity, you'll actually get something that tends to 1, namely because it's non-negative, meaning that this is bounded by 1, hence this has to tend to 1. And just by checking kind of just the parameter of this, you can see that this actually is equivalent to x ln x minus the order of this log x term, namely, and actually I can set this equal to log of x, and then hence minus the order, I said order, minus this big O of 1, hence this is equivalent, or as little o, which means that as this tends to infinity for 2 rational functions or a set of 2 functions that are elements of the rationals, or an adjoint of the Galois extension, or little o of just x log of x, and hence, because of the fact that that tends to 0, then you'll get this error term here, which hence tends to 1 for O of 1, just meaning that hence x has to be strictly this and 1 or x, for also n or x in natural number or x 1, hence for, I can also say that this is like gamma or something, so hence the limit as x approaches infinity of pi of x over x log of x is equal to 1, or gamma, or theta of x over x, and the limit is equal to 1. And we are done. I hope you enjoyed that. And